Here's a theorem about limits involving continuous functions that's sometimes useful. It says that if the limit as x approaches a of g of x is L, so that means this limit exists. To say that this is equal to L, L is some real number. So I'm saying this limit exists. It is the real number L, because it also might not exist. But if this limit exists and it's L, and f is continuous at x equals L, then the limit as x approaches a of f of g of x is f of the limit as x approaches a of g of x, which by the way is L. So you could also write this is equal to f of L. But I like writing it like this because you can see the sort of the nice way of stating this theorem sort of less precisely is just to say, well, if f is a continuous function, then this limit just passes right through it and goes inside. So you can move a limit inside a continuous function. And that works as long as when you evaluate the limit inside, the value you get is some number where this outer function is continuous. So let's use that theorem to evaluate a limit. So here's a typical example. We're trying to evaluate the limit as x approaches 0 of arctan of 1 plus x squared minus 1 over 2x. And you see there's this kind of algebraic thing in here, but then there's this arctan in front. And if I try to evaluate this limit as we usually do, you'll see what happens. First thing I should check is what happens, how does this function behave as x approaches 0? Is this even indeterminate? Well, if you check as x approaches 0, in here you're going to get 1 plus 0 squared minus 1. So this, the top in here, this numerator, is going to get closer and closer to 0 because you got 1 squared minus 1, essentially 1 minus 1, 0. And the bottom 2 times 0, you're going to get 0. So the form of this limit, this thing looks like arctan of 0 over 0. Alright, so there's this familiar indeterminate form 0 over 0, but it's inside an arctan. And so what this theorem says is, okay, all I'm going to do is move this limit inside the arctan, and the arctan is just going to stay there. And then I'm going to do all my usual limit stuff inside the arctan, and I'll be good, as long as the number I get for my limit inside the arctan is some value where arctan is continuous. So the nice thing, the way you use this theorem, you sort of move the limit in first and then ask questions later. So first thing you do is just move the limit in here. We'll do all our usual limit stuff. Evaluate it algebraically, factor, rationalize, cancel things out, all that. And see what we get. And the arctan is just going to sit out here. So in this case, you can evaluate this limit inside here just by blowing this up, expanding everything out, and simplifying. You could also use the, you could factor the top as a difference of squares. That would work too. But you could also, I'm just going to blow everything up here. 1 plus 2x plus x squared minus 1 on top. And I've got this 2x here at the bottom. Now these 1's add up to 0. And if you look at what's left over, you'll see that on the top we have a common factor of x now, so I'm going to factor it out. So x times 2 plus x over 2x in the bottom. And these x's cancel out. And so I have now arctan of the limit as x approaches 0 of 2 plus x over 2. And now in here, x approaches 0, so you're just left with the 2 over 2. So you have arctan of 2 over 2, which is just arctan of 1. And now I see, okay, in order for this step, my sort of first step, when I move this limit in to be justified, I know that this first step was justified so long as this value I got here on my inside limit is a value at which arctan is continuous. But if you look at the graph of arctan, maybe I'll remind you, the graph of arctan looks like this. It's got these two horizontal asymptotes, something like this. Goes like this. And actually, arctan is continuous everywhere on the whole real number line. So, amazing. We're done. The value of this limit is arctan of 1, and we can actually evaluate arctan of 1 exactly because, well, what is arctan of 1? You're just asking, you've got a right angle triangle here. Where this angle has a tangent, tan of that angle is 1. And so I'm asking, what is that angle? So tan of theta is 1, opposite over adjacent. So arctan of 1, it's the angle that has a tangent of 1, and, well, that's 45 degrees, aka pi over 4, right? So in the end, the value of our limit is pi over 4.